Hey everyone. We're continuing to talk about climate models and kind of how they've developed over the years, and that's really what we want to talk about in this segment. Kind of the evolution, I guess, of climate models, kind of how we got to where we are. Because obviously, if we're going to understand something, it's really important to understand kind of how it came to be. I mean, you guys have seen that over the course of this class, or I kind of always like to get into the history of things. Um, so when we talk about a modern GCM, right? Remember that's global climate model. It used to be global circulation model. Well, we're going to start with this guy. He's a Norwegian physicist, Wilhelm Birknes. I think that's pronounced. My Norwegian's not that great, right? More of a Swedish kind of guy. And he basically was thinking there's a way that we can apply math and physics to how the world works. And again, this is kind of around 1900, really long before computers. The climate on Earth is controlled mathematically by what he dubbed the primitive equations. And the primitive equations were kind of the fundamental equations that controlled how stuff moved around, how much stuff moved around, which direction and which velocity. And so just to kind of think about a shopping list, so I just kind of, I put all this out here. These are the primitive equations identified by this physicist. I'm not going to go through them, but it's worth noting that they're kind of like groups of equations. So it's not just four equations, but those equations for any particular area, this is the set of kind of mathematical sentences or kind of philosophies that describe how energy and mass move through space in Earth's system. So Newton's laws of motion. If you've taken a physics class, you've kind of done those to death. Hydrodynamic state equations. So this is essentially whether water is in the atmosphere, whether water is on land. Kind of there's a lot of evaporation and kind of humidity, I guess, built into this equation or this group of equations. The conservation of mass equation, meaning you can't lose volume or you can't lose mass going from one kind of area where the equation is calculated to another, right? Because again, we're going to start seeing that this is kind of laid out in this grid system, and so we're doing the calculation for our square to average our square, but that's going to involve things moving from square to square as the time function. And then obviously the thermodynamic energy equation. We've got energy coming in from the sun. We've got energy radiating back out to space in the form of long-wave radiation. You guys know that stuff. So these are what he sees as the primitive equations, but these equations require many, many, many different inputs and can kind of accommodate for lots of different variables. So if we were to kind of strip this down into, single word descriptions for each of these groups of equations, we've got mass, we've got momentum, we've got energy, and we've got moisture, right? So this group of equations really takes these four aspects or characteristics of that kind of section of the climate, and these will describe how that moves through. So the next thing that comes up, I find is really interesting. So our lovely Wilhelm Birknes outlines all of this and actually builds the equations, but the problem is they were too complicated. That was precise enough to solve these, so they actually couldn't be solved by the margins of error introduced by human application. Just grew and grew and grew, and the whole thing doesn't actually work if you have humans doing it. So really, kind of after World War I, so around 1920, people thought, okay, well, maybe we could do this for a small area, particularly with the thought of numeric weather modeling, right? They said, okay, well, we can take, the the Treasure Valley, and we can put this little grid together, and we can calculate these things, and we can come up with a weather model. And they pretty quickly realized that even at a very kind of small scale, right, where we're not looking at very much of the Earth at all, they're just too darn complicated. And these ideas were, seen theoretically as great. They couldn't be done. And so they were really shelved for a couple of decades. So these were basically hung up until the 1950s. In the 1950s, we had the advent of the first computers, machines that were capable of like chugging through these iterations, these round after round after round of these mathematical equations. He came up with this contribution. We didn't really have the technology to put it all together, but about 30 years later, we could start to employ computer thinking to do this work for us. So the allowing us to use computers, or kind of the availability of computers to crunch through these numbers, was really where we start to get into modern GCM capabilities, right? So actual climate modeling. Although really the first, what we would see as successful climate models don't show up until the kind of early 1970s, like 1972, 1973 is really our first model that we see as fairly successful, right? It's predicted what's going on right now. And the way that they put this stuff together is, and I'm going to show, this happens on a globe. I'm just drawing a picture of a fairly small scale. So they've basically taken a grid, or what we call a Cartesian grid, like an XY grid, and we've used these primitive equations, and we use some, at least in the 1950s, some limited inputs to basically figure out, okay, how much energy exchange, moisture exchange, how much exchange is happening. So this here shows, just a two-dimensional exchange, right? Exchanging directly with your neighbors of this kind of package of air. But that's not all, right? So actually, again, just to simplify, there's also exchange in the vertical sense, right? So these are kind of stacked that represent packages of air or climate zones at different elevations above what you would kind of see as map view, right? So maybe you're starting to get the inclination that there's a lot going on here, right? So not only is there horizontal exchange, which is really important, there's also vertical exchange and convection. And each of those little cells requires an incredible amount of computing power. So just here I've got what I drew, a 4x4, so 12 cells. You can multiply that by 3 just for my very simple model that I drew here. And now what you start to think about is when you scale out to the size of the planet, that's pretty big, right? That's a lot of computing power that we need, way beyond what we could do with human math brains, right? So the last thing that I want to talk about for this segment is, here we've seen the start of climate modeling. And like I said, I drew a small grid that might be useful for a region, right? So especially if you were kind of doing regional numeric weather forecasting. Well, just adding the term forecasting builds in this word that I've used before, prognostication, right? Like, so where do we go in the future? Which actually adds the fourth dimension, right? So not only do we have at any kind of instantaneous moment what things are moving where, how does that change as we move through time? And these early models were run with, maybe a 10 to 15 minute interval between each iteration, right? So all of the math is done kind of in one condition and then moved forward, right? Those changes are kind of incorporated. Then those changes are what are used to model from there. And those new changes are incorporated, and we kind of go on and on and on. And you can actually build your model out pretty far. But again, that starts to fall apart the farther you go and kind of the more precise of an area that you're looking at. So modern numeric weather prediction, again, like what you see when you open your phone, this is basically what it's built upon, although this is very rudimentary. It's kind of the standard for accuracy, and I mentioned this in the previous video. I always like how to joke about how the weatherman's wrong, but the weatherman's usually right, or at least pretty darn close to right. I know I plan field trips with students to go out and map rocks and things like that. I often look at rain and precipitation, and usually gives you kind of a time when that's going to happen, and that's generally pretty true. Actually, I've timed field exercises where just as we're headed back to the van, the rain starts coming down just like the weather said, right? And so that's incredibly accurate. I mean, it's also incredibly powerful, particularly, not just for me as a geology professor, but if you think about, DOD, so Department of Defense or military applications, and also agriculture. Right? All of that relies on kind of knowing what's going on with the weather. So in modern numeric forecasting, if we think about our forecast for the next 5 days, generally we're about 90% accurate within that 5 days. And what accurate means is the air is no more than 3 degrees Fahrenheit, which is 1 degree Celsius, right? So you go ahead and you say it's going to be 95 and it turns out to be 97, that's accurate. If you say it's going to be 95 and it's 100 degrees that day, well, you didn't win, right? You fell into the 10% that we see as not accurate. And these models are so accurate because they're built on today's condition, and they're really just going a few days into the future. In the next video, we're going to talk about GCM, like going hundreds of years into the future. So if you kind of go to the American Meteorological Society, this is pretty much what you're going to find out, right? So a 5-day forecast, solid, right? So for the week, but the weather guy always likes to add in the bonus days, right? So let's say it's a Monday and you want to know what the weather's going to be like on the weekend. Well, looks like I dropped a 0 there. So 80% for up to 7 days, right? Adding a few. And again, it's not that it's wrong, right? It's that it falls outside of the 3 degree accepted accuracy 20% of the time, right? So 80% of the time it's going to be within 3 degrees. It starts to get a little bit dicey when you start talking, close to 2 weeks out, right? Again, it's not that it's inaccurate, right? It might be 5 degrees off or 8 degrees off. But 50% of the time they're going to be within that margin of that acceptable margin of error. And that's pretty good, right? Especially, like I said, for kind of near-term applications like agriculture, military, or recreation. Okay, so that kind of built us through, someone who develops equations that we can't solve as people, us overcoming that and inventing machines that can solve those, using those to help us learn the weather. Talked about this Cartesian grid system, and now we need to take that and basically scale it up to the size of the Earth, right? And really see how far we can run a GCM into the future, what sorts of accuracy we could expect, and what sorts of accuracy have we seen, right? So like I said, we started running these models in the 70s, and here we are, in 50 years later, 50 or 60 years later, how well did those predict where we are today? And you might be surprised. All right, see you in the next video.